Photoelectron Spectroscopy, or PES, provides experimental evidence for electron configurations. In a PES experiment, energetic light removes electrons from atoms. The energy required to remove an electron tells us how strongly that electron was attracted to the nucleus. On a PES spectrum, peak position represents binding energy, while peak size represents the number of electrons. Keep these two meanings separate. Peak position tells us attraction, and peak size tells us electron count. Follow the process from left to right. First, the instrument sends a photon with a known energy toward an atom. Second, the photon ejects an electron from the atom. Third, the instrument measures the kinetic energy of the ejected electron. Binding energy equals the energy of the photon minus the kinetic energy of the electron. A larger binding energy means that the electron was held more strongly. A smaller binding energy means that the electron was easier to remove. Always check the direction of the binding energy axis. In most PES diagrams, high binding energy is located on the left, while low binding energy is located on the right. This may feel backwards. Core electrons are located close to the nucleus and appear on the high binding energy side. Valence electrons are easier to remove and appear on the low binding energy side. Some spectra use a logarithmic scale, so equal distances on the graph may not represent equal differences in energy. Each main PES peak represents an occupied electron sublevel. The 1s electrons form one peak. The 2s electrons form another peak, and the 2p electrons form another peak. The same pattern continues for higher occupied sublevels. Therefore, the number of main peaks tells us how many sublevels contain electrons. An empty sublevel does not produce a peak. Start by counting the peaks before trying to identify the element. Peak position represents the strength of attraction between electrons and the nucleus. A stronger attraction produces a higher binding energy and moves the peak toward the left. A weaker attraction produces a lower binding energy and moves the peak toward the right. Nuclear charge, distance from the nucleus, shielding, and orbital penetration all influence binding energy. Within the same principal energy level, an s electron generally penetrates closer to the nucleus than a p electron. Therefore, an s electron is usually more strongly held. Peak area represents the number of electrons occupying a sublevel. A filled s sublevel contains 2 electrons, while a filled p sublevel contains 6 electrons. Therefore, the area of a filled p peak is approximately 3 times the area of a filled s peak. Simplified PES diagrams sometimes use peak height to represent electron count. However, integrated peak area is the more reliable measurement. A larger peak means more electrons. It does not necessarily mean that the electrons are held more strongly. Magnesium has the electron configuration 1s2, 2s2, 2p6, 3s2. 4 sublevels are occupied, so its PES spectrum contains 4 main peaks. From high to low binding energy, the peaks represent 1s, 2s, 2p, and 3s. Their relative electron counts are 2, 2, 6, and 2. Therefore, the 2p peak is approximately 3 times the size of each filled s peak. The 1s electrons are closest to the nucleus and experience the least shielding. They are therefore the most difficult electrons to remove and have the greatest binding energy. Electrons in the second energy level are farther from the nucleus and are shielded by the 1s electrons. Within the second energy level, the 2s electrons penetrate closer to the nucleus than the 2p electrons. Therefore, 2s generally has a higher binding energy than 2p. The outermost valence electrons have the lowest binding energy. Now compare electrons in the same sublevel as we move across a period. The number of protons increases, while shielding remains relatively similar. The electrons experience a greater effective nuclear charge and are attracted more strongly to the nucleus. As a result, the corresponding peak moves toward higher binding energy. Remember that peak position and peak size provide different information. Peak position represents attraction, while peak size represents the number of electrons. Neutral sodium has the electron configuration 1s2, 2s2, 2p6, 3s1. Therefore, its spectrum contains a small 3s peak. When sodium loses its 3s electron, it forms a sodium ion. The 3s peak disappears because that sublevel is now empty. the remaining electrons are also attracted more strongly because the same number of protons is attracting fewer electrons. Therefore, the remaining peaks generally move toward higher binding energy. Use 3 steps to analyze an unknown PES spectrum. First, count the main peaks to determine the number of occupied sublevels. Second, compare the peak areas to determine the relative number of electrons in each sublevel. Third, use peak position to distinguish core electrons from valence electrons and compare their attraction to the nucleus. Finally, write the complete electron configuration and check whether the total number of electrons is reasonable. Consider this worked example. The spectrum contains 4 main peaks, so 4 electron sublevels are occupied. From high to low binding energy, assign the peaks as 1s, 2s, 2p, and 3s. The 2p peak is approximately 3 times the size of each filled s peak, so it represents 6 electrons. The relative electron pattern is 2, 2, 6, and 2. These values add up to 12 electrons. A neutral atom containing 12 electrons is magnesium. Now try this question. An unknown PES spectrum contains 3 main peaks with relative areas of 2, 2, and 1. Which neutral element does the spectrum represent? Option A, beryllium. Option B, boron. Option C, carbon. Option D, nitrogen. Use the number of occupied sublevels and the relative electron count in each sublevel. Pause here and select one answer before continuing. The correct answer is option B, boron. 3 peaks mean that the 1s, 2s, and 2p sublevels are occupied. The relative areas of 2, 2, and 1 give the electron configuration 1s2, 2s2, 2p1. This configuration contains a total of 5 electrons. Therefore, the neutral element is boron. Now compare sodium and magnesium. Which statement is correct? Option A. Sodium has the higher 2p binding energy. Option B. Magnesium has the higher 2p binding energy. Option C. Sodium has the larger 3s peak. Option D. Their 2p peaks must appear at exactly the same position. Consider nuclear charge when comparing peak positions and electron count when comparing peak sizes. Pause here and select one answer. The correct answer is option B. Magnesium has the higher 2p binding energy. Magnesium has 1 more proton than sodium, while the shielding experienced by the 2p electrons is relatively similar. The stronger nuclear attraction moves the magnesium 2p peak toward higher binding energy. Magnesium also has the larger 3s peak because magnesium has 2 3s electrons, while sodium has only 1. Here's another question. 2 spectra represent neutral sodium and the sodium ion. Which statement correctly identifies neutral sodium? Option A, the sodium ion has a 3s1 peak. Option B, neutral sodium has no 3s peak. Option C, neutral sodium has a 3s1 peak. Option D, both spectra contain a 3s1 peak. Think about which electron sodium loses when it forms a positive ion. Pause here and select one answer. The correct answer is option C. Neutral sodium has a 3s1 peak because its electron configuration ends in 3s1. When sodium forms a positive ion, it loses this outer 3s electron. Therefore, the sodium ion does not have a 3s peak. The remaining peaks in the sodium ion also tend to move toward higher binding energy because the remaining electrons experience a stronger attraction. Try one final question. Peak A represents an s sublevel containing 2 electrons. Peak B has 3 times the integrated area of peak A. How many electrons are represented by peak B? Option A, 1 electron. Option B, 2 electrons. Option C, 4 electrons. Option D, 6 electrons. Use the direct relationship between peak area and electron count. Pause here and select one answer. The correct answer is option D, 6 electrons. Peak area is directly proportional to electron count. Peak A represents 2 electrons, and peak B has 3 times the area. 3 multiplied by 2 equals 6. A peak representing 6 electrons is consistent with a filled p sublevel. When the widths of 2 peaks are different, compare their integrated areas rather than their heights alone. Here is a reliable strategy for solving PES questions. First, count the peaks to determine the occupied sublevels. Second, compare the peak areas to determine electron counts. Third, use the peak positions to compare binding energy and attraction. Do not confuse peak size with binding energy. A larger peak means more electrons, not necessarily a stronger attraction. Finish by writing the complete electron configuration and checking the total number of electrons. To finish, remember the three types of evidence provided by a PES spectrum. Peak count identifies occupied sublevels. Peak area identifies relative electron numbers. Peak position identifies how strongly the electrons are held. Assign the peaks from core electrons to valence electrons. Write the electron configuration and check the total number of electrons. For multiple choice questions, eliminate any option that confuses peak position with peak size.